Hello everybody, my name is Markus Nispel. I run the R&D team for our cross-portfolio applications. Cross-portfolio applications is most of the things that you have seen: network management, network automation, workflow automation, security, access control, analytics, ecosystem integration. What I will do is take you through a brief journey on how we think about network management and network automation, and then dive into a project that is in flight right now, which is our security analytics and threat response capabilities. And specifically there, I'm going to talk about some of the new ingredients that we layered on top, which is a machine learning driven anomaly detection capability. And I'll dive deeper into that as well. Yeah? So just in general on how we think about the platform. So what you're seeing, Extreme Management Center is a term, but it's really a platform that basically hosts all of our cross-portfolio applications. What we are really trying to do is we are trying to develop a platform that provides you with complete network lifecycle management. So what is complete network lifecycle management? We are trying to stitch together day zero planning, day one deployment, day two operations, as well as optimization along the way. So you're really able to define your network design and configuration in the platform itself. So that's step one, define intent and design, so configuration and policies at the same time. Wired, wireless, access, data center, doesn't really matter. Then we go into an automated deployment. You plug in your devices, wired, wireless, it doesn't matter. They find their configuration repository and get initially provisioned, zero-touch provisioning, so truly zero-touch provisioning. Then you enter day two operations, you add or remove services, you add or remove policies, you add or remove devices. That's all pretty straightforward. Everybody does a little bit of that. We think we have a nice integration of those. But then you enter the analytics and insight phase. Yeah. So what you've seen before is more or less data presentation, but from an analytics perspective, you want to go deeper and you want to automate the processing of that data. So as the amount of data that you're going to see in such a platform is pretty high, you need to start to automate also the analytics part, and that's where machine learning kicks in. Yeah? Yet another buzzword, but I will be very specific on what we do in that space today and what we envision to do moving forward. You need to automate that because only if you have automated the insights, then you can automate the remediation part. So how do you optimize your network? How do you react to changes? How do you react to anomalies? How do you react to threats? That needs to be automated as well. Once you close the entire loop, you basically have more or less an autonomous network. So you're hands off ultimately. Nobody wants to do that today. It's like autonomous driving. Sounds good, but we start with lane assistance, parking assistance first, and once you feel comfortable, you might be hands-off at one point in time. And similarly, we look at network operation and management the same way. Yeah? So keep that in mind. So ultimately, we want to go from this. Yeah, we are basically today somewhere here between UI and API, so automation-driven, to an AI-driven network. And any of our customers should be able to move and evolve that at their own pace. So that's basically our perspective on how we develop our platform. Yeah? Prasad talked about that already. As part of the automation, it cuts down provisioning time. Something that took 10 days before is now down to 4 minutes in terms of cross-domain automation and integration. So that's something that we are driving as well by integrating additional capabilities that we got and acquired through some of our recent acquisitions, so Workflow Composer specifically. So on the management side, just getting back to day one, so we do have a structure, and Steve talked about that already, that we call sites. So site is your network hierarchy where you lay out your network, and you also lay out your network configuration. Network services, VLANs, VRFs, VNIs, VXLAN, VNIs, IP addresses, and things like that. And once you have done it, devices as they attach to the network get provisioned using that kind of capability. The whole structure is developed in a way that you can automate also the creation of those sites and the configuration underneath. So we use GraphQL, which is an evolution to REST to do that on the northbound side. On the network provisioning side, we use a mesh of REST, RESTconf, CLI scripting, SNMP, whatever the underlying device can provide. But on the northbound side, we abstract all of that. So you as a user in the UI, or you as a user on top of it through an API, you don't really see what we're using underneath to provision the infrastructure. And that applies again to wired and wireless. Everything that is not natively supported in our product, you can basically work around it and stitch around capabilities using our embedded workflow engine that then can also call into Workflow Composer for more cross-domain automation as well. So those two are tied together, and that will be also part of the demo. So you're going from network automation to cross-domain IT automation in one architecture, in one product. Yeah? So we covered that already, so I can skip the Workflow Composer side. A lot of capabilities. What we're going to show as part of the demo is a Jira integration, so you can automatically generate Jira tickets. You can do it with ServiceNow, whatever you want to. The point is, it's much more than just network automation, so it really ties together the entire IT stack, yeah? In one solution. Yeah? Another component that is part of the automation framework doesn't come up immediately, or it doesn't come immediately to mind that it's a critical component, is our access control solution. That's also part of the demo that we're going to do. So access control for us gives us two capabilities. One is obviously security, secure onboarding of users and devices. On the other hand, it allows us to automate the edge entirely. Yeah? Prasad hinted on that. If you think access control, think about edge automation. Yeah? You plug in a user device anywhere on the network, services get provisioned, and what we do is we basically extend that policy mapping and that service provisioning throughout the entire core using our Fabric technology. So it goes nicely together. So from that perspective, Fabric, access control, policy is, from our perspective, the perfect marriage of technologies in one solution. Yeah? So we detect new devices, we authenticate them using different mechanisms. We can do endpoint assessment, we do authorization. That is also abstracted in a way that we can support any kind of access device, whether it's our gear or our competitor's gear, yeah, or a mix of both. Again, we are trying to abstract the operations to a point that it doesn't really matter what infrastructure is underneath. So from an operator's point of view, it looks the same. Yeah? And then you enter the monitoring phase, leveraging analytics, and then you can start doing very interesting things along the way. And again, that will be part of the demo. Huh? So I mentioned that stitching together automated access layer provisioning using access control and policy and mapping that to Fabric technologies. We think that's the perfect marriage to provide hyper-segmentation in the network, to provide edge automation, and to provide the ability to quickly roll in new services into your network infrastructure. Yeah? So it was just a compressed version of how we are looking at the platform. So really important, automation and analytics are going to get married more and more together, and that gets you to a fully automated and autonomous network operation. Yeah? In 2019, I mentioned it before, we are in fly developing a solution that is layered on top of Extreme Analytics, what Ranjan and Steve have shown you before. That is heavily focused on security. Ranjan mentioned it before. If you look at our analytics platform and application telemetry, there are three main use cases: IT operations, business analytics, as well as security analytics, and then obviously threat response. And that will be the focus of the remaining part of that presentation. Security analytics, obviously there are different types of devices and users in the network. We do have capabilities to detect threats coming from each and every of those. What we are going to show later here is focus on IoT devices, because we feel that they are the least protected today. Hopefully everybody for a managed desktop has an idea to how to secure that. For IoT, it's really tough for our customers to get a handle on what's happening, the amount of devices that get enrolled, the level of non-security that those devices have, lack of patch management, lack of endpoint management, basically old and stale OSs that don't see and experience any security patches anymore. We feel that, especially in the IoT space, there's the biggest need to provide additional security capabilities, and that's basically what we are focusing on initially. And as the scale is tremendous, also, again, we need to be able to automate the detection of anomalies and threats, and also automate the response towards those. And that's at the core of our security analytics and threat response solution that we are working on. So how do we do that? A little deep dive into the underlying mechanisms. Machine learning is obviously one of the big buzzwords these days. Everybody has it on their data sheet. But what do we do specifically? So we think we have a very unique approach to it to address basically the concern that I just laid out. And the fact that this is a challenge is shown in a report here from FireEye from last year that really represents the dramatic change in terms of the amount of days and time it takes to detect a threat on the network between just 2016 and 2017. So the number of days almost doubled. So a lot of devices get compromised, nobody detects it. That's a problem. So how can you be within monitoring, so within the reactive part of security, how can you still be very proactive? And that's what we are trying to address with our solution. Talked about that, so we will address IoT first, IoT devices first, and then go to human-driven endpoints. So IoT, because it's the biggest exposure, and also IoT is easier to grasp. An IoT device typically has a much more deterministic behavior than a human-driven endpoint, so it's also easier to apply certain algorithms and technologies to it. So basically, we are trying to address that. Everybody knows what that is? Yeah, Raspberry Pi. So if you have one of those, temperature sensor, for example, it's pretty easy to figure out what that thing is doing. So you have an NTP connection, you have HTTPS connection that's probably just sending the data back to a cloud platform. You have some SNMP, that's it, pretty straightforward. But you don't have one of those. You have at least 8, maybe more. Maybe it looks like this, but in reality it looks something like that. Yeah. So that's what you have. That's what our customers have today on their network, more or less. And how do you figure out? Did you see that? How do you figure out that this guy is behaving differently? Yeah? So that's basically the trick. Yeah? And going back to what I said before, the amount of data that you're going to see is so high that you can't do it manually. So you need to use machine learning. Yeah? If you look at most techniques today around machine learning and anomaly detection, they require a lot of processing power and a lot of storage. Basically, what you do is you feed your data to the cloud or some huge compute cluster. You're storing data for a very long time. You're trying to crunch it, so you need a lot of CPU. CPU means cost, so our friends from Amazon, Google, and Azure are happy about that. And at the end of the day, you have a model that you then download to your devices, and the model is trying to figure out what's going on. So instead of going down that route, we said, hey, there must be something easier and simpler that we can do using a creative combination of existing technology. So the goal for us was, how do we do online learning? Yeah? How do we do learning in real time in an unsupervised fashion that doesn't require those large and expensive storage and compute backends to pre-calculate the model and then download the model down to your devices. So the solution that we have developed doesn't need storage, huge amount of storage or compute. And also, as we describe the behavior of a device through those mechanisms, we also don't need to store user-sensitive data. So GDPR and data privacy is everywhere. At the end of the day, our algorithm doesn't require those specific details to run on our appliances. So being online and being very efficient around compute and storage resources, that's at the key and core of that technology. Yeah? It's being inspired by natural language processing. So it sounds really weird. So what does natural language processing have to do with network security? Natural language processing goes back to a concept out of the 50s, and John Rupert Firth brought that first up. You shall know a word by the company it keeps. So you can infer certain relationships between words in a language based on the neighboring word. Yeah? Very abstract. In the last few years, specifically, Google and Facebook have published a lot of papers around natural language processing on how to automate that. And they also published a lot of tools that are supporting that kind of technique. So it allows you to basically take a language and transform that into the digital world, into basically vectors in a multidimensional space. Yeah? And while you do that, while you learn your language, you are able to predict the next word based on the neighboring words. So that's how you're going to learn a language ultimately. Yeah? And once you have done and you have ingested all of that, you can do interesting things. Yeah? So that's basically the ingestion part. So you get a multi-dimensional vector space that you can use to do interesting inference. For example, if you look at any language, once you have figured out the relationship between two related words, and the relationship is measured in vector distance, depending on how many dimensions you have, that's tricky to calculate. But ultimately, if you know the distance, vector distance between king and queen in English, you know already the distance between male and female. So you can learn new words by just applying a vector against a word that you know already. Yeah? And you can do that male, female, past, present, or you can do it based on countries and capitals. So that's the underlying technology. So it's very well proven, has been out there for quite a while. So what does it still have to do with networking and security? Yeah? So we invented basically an artificial language, which is how we describe our flows in the network. So each flow, at the end of the day, is a word. And each endpoint producing those flows basically creates those flows in a book that becomes a document. So each endpoint is ultimately a document. Again, with a number of vectors that we calculate, and from those words we average those out onto each endpoint. So each endpoint is described in a multidimensional space with its behavior through that language. That's basically the base for us to then detect a behavior change. Yeah? So what you see here on the right-hand side is basically a graphic of the dimensions that we calculate for each and every endpoint, and whether what we see in terms of flows is aligned with our expectation. And our expectation is calculated by creating a exponentially weighted moving average of each vector within, or each vector of those 500 dimensions that we're using for each endpoint. So at the end of the day, we look at each vector and each distance for each endpoint and see how it changes over time. And that is being modeled out, and if there's a radical change, so to speak, so we are outside of an expected range, then we're going to create an event. So we see an anomaly. Pretty straightforward. Sounds very compute intensive and memory intensive, but it's not. So at the end of the day, each endpoint and basically the entire document that describes the behavior of that endpoint with its flows is less than 5 kilobytes. So we can model at the same time millions of endpoints on a general x86 compute platform on-prem. There's no cloud involved. There's no huge memory footprint involved. And that's at the core of our unique technology. Yeah?
What's the time frame when you're talking about this? So I mean, I think about these anomalous flows, yep. These things, okay. A great example is like a payroll system or something that does something that only does it once a month or does it something like that. Yep. Would that constantly show up as a flow anomaly, or are you going to be able to add that to your profile over time?
two answers to that. So for those, so we basically keep a sliding window of that moving average and trying to compare every new calculation that we do, which typically happens every minute or so, depending on the flow rate coming in, against the moving average. So if you have an outlier like this, there are two solutions. You can whitelist that based on time, or you can use another technique that we are working on, which is fuzzy clustering, which comes out of, some people use it for electronic microscope sharpening of the picture. If you do that kind of clustering, you can figure out those new flow clusters, so to speak, and you can also whitelist them out to avoid those periodic anomalies. Yeah.
Also, are you doing anything in your system here that is fingerprinting similar hosts to help reduce the computational load?
That happens automatically. If you look at two endpoints using similar flows, they will have similar vectors, so they will be clustered. You will see that later in the UI. So they are clustered. So we know, and you will see it in the UI as well, that devices of similar behavior are in the same cluster space. Yeah? Initially, we thought we use the distance between same device types within the cluster to measure it, but it turned out that the technology that we're using here to detect an anomaly is more accurate and also doesn't create cluster dependencies in that space. Yeah, but yes, yeah. So what you see here, just as you look at the picture, so the top picture, everything is on a per endpoint base over time. So what you see here is basically the variance of a new vector versus the moving average that I said before in terms of distance. Yeah? As we have our threshold on how much that vector can differ from the previous one, we basically make a yes and no decision. Is that dimension in that vector still within range or not? You get a yes-no type of scenario over time. And if you then aggregate the micro anomalies per vector and count those up, you just see, hey, at this point, this device has shown an anomaly, and that creates the event that triggers everything. Yeah. Yes?
What do the dimensions represent here? Is it different metrics on the same flow?
It's different metrics on the dimensions itself is describing the flow itself and its words. So every dimension gives you an idea of an attribute or a component of that flow. Yeah? So it's also tricky how many dimensions do you create. Do you go less or more? I can tell you that per flow, we have hundreds of dimensions that we calculate to get proper accuracy. Right now, we started with 300. We are leaning towards 500 dimensions. Compute-wise, it almost doesn't make too much of a difference. And storage-wise, obviously, 300 to 500 is a little more, but it's still in the kilobit range per endpoint. Yeah. But it describes more accurately the sum of flows and words that are associated with an endpoint. Yeah. The more you have, the more dimensions you have, the more granularity.
But basically, you're increasing the observation window and the more neighboring words.
The observation accuracy, not the window. The window itself is every time
I didn't mean
we
the
see
time window. I meant the depth at which you look at the neighboring.
It's more the depths. Yeah, correct. Yeah. What we also want to do on top of it, so what I mentioned before, we have clustering within the algorithm to basically get the once-a-month software update probably covered. We're looking at fuzzy clustering as a technology layered on top of that, which is still very lightweight, but then you can really figure out which flow created an anomaly, and you can do additional higher order reasoning on top of that. But again, that's probably beyond this presentation. Yeah? So once you put it all together, using application telemetry and the different detection mechanisms, so beyond the machine learning engine, we also have other ways to detect threats in the network. So I would say the traditional ones. So we have a reputation feed that we integrate from Alienwall to get domains, URLs, IP addresses, malware domain list, emerging threats, credential scan, what you've seen from Mirai and other botnets. We can stitch that all together, make a call, whether you want to respond to it, and that call to respond to it can be based on just sending an email, hey, there's something wrong, go out and check it out. Hey, trigger a packet capture, so everything is event-driven internally in the system. So what Ranjan showed before, an event that describes an anomaly could trigger a packet capture. So again, a security analyst can take a look at it and say, okay, that's good, that's bad, do something about it. You can blacklist the device. Blacklist means change the policy on the fly, which is part of our access control system. So we have basically a real-time view of all endpoints connected to the network. So we know who they are, where they are. So you can flip policy on the fly. You can create a trouble ticket. You can block the flow at a firewall. You can rate limit it. Or you can do all of the above, depending on user, device, location, time of day, event type. So that's the idea. Yeah?